Afternoon, everybody. I don't know why I'm waiting for the delay. It doesn't help. There's still a delay after I wait anyway. um, uh, Stream seems to be good. Let's start the recording. Alright. Welcome everyone to the Week 5 lecture for Programming Fundamentals 2021, Autumn 2021, because we'll run next semester as well. To answer the chat's question, today we have a black tea. So anyone who went for green, sorry, you're wrong. Not this week. It is in fact a Darjeeling. So a fairly straightforward one, not a first flush or a second flush or anything, just a generic box of Darjeeling tea. But to be fair, Darjeeling is relatively close to green tea, at least as much as black tea can possibly be. Okay, so that's the important question out of the way. We can stop the lecture. No. So we've been looking the past couple of weeks at arrays, loops, arrays, loops, loops, arrays, arrays, loops. We've just started to touch on methods. But before we go any further, as those of you who have looked at the lessons will have seen, what I want to look at is sort of our first, well, it's not that we haven't been doing practical things so far, but they've been very small things that kind of don't make a whole program in themselves. They're components of a bigger program. What I want to look at this week is sort of our first thing that we can write as a whole program that does something useful in and of itself. It's not the most massive program in the world, but it is fundamental to an awful lot of things that we do in computer science. And those who've read the lesson will know that this is about searching and sorting. So once we've got loops and once we've got arrays, we can write generic searching and generic sorting algorithms. Yeah, like Hello World is a whole program, and to be fair, that is basically used in the Python REPL to tell you to put how to actually get out of the REPL, but nonetheless, it's a small component of the bigger program. So we've actually already been doing a bit of searching already, in that we've had arrays or collections of data and we've been looking through them to find something. We haven't been doing searching in sort of a formal way, but we've kind of seen it, and there's kind of an obvious way to do it. If you've got an array, you can move along until you find the thing that you want and then do whatever it is you want to do with it. So mostly what I want to spend my time on in this lecture is two sorting algorithms, and sorting is a really, really fundamental tool in computer science. There's a good rule of thumb, slightly tongue-in-cheek, but nonetheless, it exists, that when you're writing a program and you don't know what to do, sort your data. Just the first thing, sort it. It's probably going to be easier if it's already sorted. So sorting data is hopefully it's obvious that it's pretty useful, but it's very useful in that once you've got sorted data, you can make a lot more statements about your data set by doing a much, much smaller number of queries in the general sense. So it's related to database queries, but I just mean like looking at the data. So if it's sorted, it's easy to find the minimum element. You just look at the first thing. It's easy to find the maximum element. You look at the last thing. It's easy to compute certain statistics. So if you've got the biggest and the largest, and you can get them like that, because all you've got to do is look at the first thing and the last thing, then it's just a simple calculation. It gives you the range of values that it's in. You can immediately know if a certain value is even possibly there. So if it's bigger than the largest thing or smaller than the smallest thing, you know it can't even be there. It also makes searching easier. So if your data is sorted, So those of you who have read the lesson already will have seen binary search. If your data is sorted, then we can find something in that data effectively exponentially faster than we can if it's unsorted. Let me just put the background back on. Because once it's sorted, we don't need to... sound stuff. Yeah, we don't need to look through everything to find something because we don't know where it is. Once it's sorted, we do know where everything is. So if we look somewhere and the thing we're looking for is smaller, we know to look in the earlier part of the array. If it's bigger, we know to look in the later. And you can turn this into a very effective algorithm. And binary search on sorted data is also a fundamental tool. Right. So, again, if you've read the lessons already, you'll see that what we'll look at in this subject is two fundamental sorting algorithms. Where do I want to go? So if you've read that and jumped over to the Wikipedia link that I put in there, my webcam's like, yeah, right. It does that. I'm taxing my system at the moment. You'll find out why in a moment, because I've made a hacked up fun, hopefully fun thing to do. If you've had a look at the Wikipedia thing, like I said, you'll see there's a whole bunch of different sorting algorithms that have a variety of different properties about them which make them more or less attractive in different situations. So when you get to data structures and algorithms, for those that are going that far, you'll actually look at a few of these. Not everything, obviously, because most of them are very particular in their applications. But you'll look at a few of these and start to understand which you would choose in certain situations and what all this nonsense with this n log n and stuff means, which we won't cover in this subject at all. So this is just for edification. It doesn't, you don't have to learn this. Ooh, that's really hot tea. So the ones that we're going to look at are selection sort and bubble sort. These are not the best sorting algorithms in the world, but they are some of the simplest. And you already have, after, what are we, not quite 6 weeks of learning how to program, enough skill to implement these, and they are still good enough to work reasonably well. So we don't need anything tricky to do these, and we can already achieve a really important goal in programming, which is sorting data. Okay. Well, we can do BOGO sort really quickly. We'll try BOGO sort in a minute, but not yet. So let's see if what I've rigged up works. Hey. So this is why my webcam is lagging, because I'm running another one. Let me just move the microphone. Ooh. Right, so here's my exciting, super dodgy document cam. Someone turned a light off, it got darker in here. I'll work out lighting next week. So what I want to do here is something that used to be done in programming fundamentals live with people. And that's actually enacting a sorting algorithm physically. Obviously, it's a bit tricky to do with everyone in different spots. So I thought I'd have a go at doing it like this. So this is a bit experimental, so bear with me. So what we've got here is an array of 6 elements. They happen to be 0 to 5, but that doesn't matter. And the questions and stuff are over there. I'm going to have to do a bit of running backwards and forwards to get this to work, but it'll work. So we've got an array of 6 elements, and what we want to do is sort them. Now, obviously, as humans, we can very quickly go, okay, put 0, 1, 2, 3, 4, 5. Super easy. But that's a bit of a trick, because we've got human brains which do a large amount of basically parallel processing. Right, so we've got our visual field, which allows us to look at a whole bunch of information all at once, and then do some processing on that and do things like sort small amounts of things. If I had like 20 or 30 numbers here, however, that would suddenly become much, much harder. So the human brain can handle, give or take, 7 things at once with a standard deviation of about 2 elements or something like that. So some people can handle 13 or 14 at a push, but most people can handle about 6 to 8 things. So let me randomize the array. See now? Just going to check the comments to make sure this isn't lagging too much. Okay, hopefully this is still working as nice as it looks on OBS, which is of course my local display, so I've got no idea what the stream looks like. Ooh. Sorry, YouTube's just complaining about it's not receiving enough video to maintain smooth streaming. Sorry, just doing some live stream adjustments here. Okay. Okay, so it looks like the uni internet connection is a bit patchy at the moment. I don't quite know why. So those who are watching on the stream, sorry, don't think there's much I can do about the frame rate at the moment. Hopefully it'll pick up shortly. So if it's terrible when I review it later, I'll replace it with the recording, which is all recorded locally, so that'll be much, much better. It's annoying, this was my big exciting reveal. Okay. Anyway, so I'll just go relatively slowly, so even at 5 frames per second it should get something out. And just to check, everyone can hear me okay, right? Okay. Yeah. As long as you can hear me, at least the recording will be good later. So, what we've got here is an unsorted array, and we're going to apply two different algorithms to sort it. So we're going to sort it one way, re-randomize it, and sort it again. So what I'm going to start with is bubble sort. So the basic idea of bubble sort is really, really simple, and that is its main advantage. It basically has incredibly simple code. You don't know it yet, but you've actually done throughout the exercises in the labs all the individual components of this algorithm. So the way that bubble sort works is that it just progresses along the array a pair at a time. If they're in order, so if the one to the left is less than the one to the right, then everything's okay. It works fine. Ooh, the stream's come back. Frame rate should be a little bit better from now on, hopefully. If they're out of order, so like these ones, it swaps them. And it just keeps going along the array over and over again until it gets through the whole thing without swapping anything. So, to make bubble sort work, we need a variable that's a boolean that just tells us whether we've swapped something or not. So I'm off camera there. So far at the start we've had no swapping. We haven't swapped a thing yet. And what we're going to do is one by one compare adjacent elements, and if the one to the left is bigger than the one to the right, we're going to swap them. So here in our starting array, 2 is less than 4, so 2 is not greater than 4, because it's less than it. So we don't swap anything, that's fine. We don't change our swap variable down here, because we haven't swapped anything. And then we move on to the next pair. So as the algorithm down here says, we swap the disordered adjacent pairs until you can't swap anymore. So now we look at 4 and the one after it, 3. If 4 is greater than 3, then we swap them. So 4 is definitely greater than 3. So we swap those two elements. There's something slightly better than post-it notes for this. Now we've made a swap. So we've changed something in the array. So we change our little boolean variable to saying that we've swapped something. And then we move along to the next pair. So we're going to compare 4 and 0. If 4 is greater than 0, then we swap them. So 4 is greater than 0. So we swap those around. We set swap to true, but we've already done that, so it now remains true until we're done. Well, not until we're done, until we finish this loop through. Then we compare the next pair. So 4 is greater than 1, so we swap them. So you can see maybe at this point why it's called bubble sort, because you've just seen 4 bubbling its way up the array. And you can also maybe at this point see why you have to keep going through the array over and over again, because this 0 and 1, which should be at the start, have just moved down one spot. So because of the way it works, it basically at each loop through moves the next biggest thing to the end of the array, and everything else shifts down one. Okay. So we swap there, set that to true. Then we compare these. 4 is not greater than 5, so we don't swap them, but we look at our swap thing here. We have swapped, so we go back to the start, and begin again. So once we manage to make it through a whole run of this without this ending up as swap by the end, then we're happy and the array should be sorted. So 2 is not greater than 3, so we don't swap, and we don't change this variable. That's fine. 3 is greater than 0, so we do swap. So you can see 3 is starting its progress up the array. And we've now swapped something. So then we look at the next pair. 3 is greater than 1. So we swap them, set that to true, which is it already is, and move up. 3 is not greater than 4, so we don't swap them. And in the unoptimized version of the algorithm, we check the last pair again. Technically, you can do some fiddly stuff where you keep track of how many times you've been through, and you know that at each pass through, you'll have moved the next biggest up to the end, so you can slowly make it a bit quicker each time. But anyway, we've made it to the end and we have swapped something, so we go back to the start. Yeah. I need to make like little tokens for these. So 2 is greater than 0, so we swap it. And we've swapped something, so we set that back to true again. Move along. 2 is greater than 1, so we swap. Set that to true. 2 is not greater than 3, so we don't swap anything. 3 is not greater than 4, so we don't swap anything. 4 is not greater than 5, so we don't swap anything. But we have swapped something, so we have to go all the way back to the start and do it all again. So we set our swap variable to false, or here, no swap. Then 0 is less than 1, so we don't need to swap anything. So this stays as false, or no swap in this case. 1 is less than 2, so we don't need to swap anything. 2 is less than 3, so again, still don't need to swap anything. 3 is less than 4, still don't need to swap anything. 4 is less than 5, don't need to swap anything. So we've made it all the way through the array without swapping a single thing. So if we get to here and this still says no swap, we stop. So the algorithm at this point is finished. And as you can see, here's our beautiful sorted array 0 to 1. Okay. So that's bubble sort. It's swap adjacent pairs until you can't swap anymore. So let's take a quick look. Steal the microphone back. So let's take a quick look at a sketch of what the code looks like. So again, for those who've read the lessons, you'll know that next week's required ones, sorry, lost my tea. Next week's required ones are actually implementing these algorithms, so I'm not going to give you straight out the code for this immediately. So I'm just going to write it in text. So our input is an unsorted array. Our output is a sorted array. And I need to change my thing. Like my transitions, by the way, pretty exciting. And then we have a variable called something like swapped. So I'm going to write this in weird old pseudocode. Oh no, that transition was not the bitrate dying. That was me deliberately picking an awful transition. Yeah, and yes, I know I'm assigning this twice immediately, but you'll see why in a moment. So let's give the array a name. So this is our basic algorithm here. We keep doing the swapping while something has been swapped. Sorry, that'll make it actually work. While something has been swapped, so we assume that something needs to be swapped. Then when we write at the beginning, we say we're going to be hopeful and say that we haven't swapped anything. I mean, we haven't swapped anything at that point, but we're going to hope that it stays the same. Then we go along the array and compare the adjacent pairs. If the earlier one is bigger than the one just after it, then we swap those two. And we set our swapped variable to true. So that goes all the way along the array and gets to the end of the for loop. And maybe it's made some swaps, maybe it hasn't. If it has, swapped will be true. If swapped is true, it does the whole thing again. It goes back to the beginning and repeats it over. So in some ways, it's a very, very dumb algorithm, but this is basically the code. Again, what I'm giving you here is pseudocode that looks... What language is this in? This is kind of Pascal, kind of Algol, with a dash of Fortran. So I might as well just use the Java one then, sorry. That's my old reflexes kicking in. The colon equals is just the traditional pseudocode assignment operator. Mainly to distinguish it from using equals as the comparison operator, because when you write it on a piece of paper, it's not always obvious that there's two equal signs next to each other or something like that. But because you've got the workspace here, I'll leave it as the Java one. And that's basically it. That is bubble sort. So this is, I mean, genuinely, if you write it in Java, there is, like, depending on how you do it, maybe one or two more lines of code. So you've got an entire sorting algorithm. This will sort any length of array that you give it that works in, give or take, 6 to 10 lines of code. It is not the most efficient sorting algorithm, but it gets the job done. So if you've got a situation where you need to keep the code in a very, very small space, bubble sort is quite useful. The other advantage of it is that it's pretty hard to get it wrong. You either get it catastrophically wrong or it works. And if you get it catastrophically wrong, it's probably not going to compile. But once you get it right, you've got a working sorting algorithm really, really quickly. So just to go over those again a little. And for the... Hang on. Let's make this really old school. And if... So, if you dig into old programming languages, before you get the algol curly braces and various other things, one of the ways of indicating the start of a construct was by a keyword. So what we see in Java is a while loop, where it's while, open parenthesis, condition, close parenthesis, open brace, code, close brace. Often in pseudocode and in some old languages, you get while, condition, do, then the code, and then an end while at the end. So to answer the question, you don't need a colon at the end of each line. I'm making the pseudocode up as I go along. I can do whatever I want. I literally just had a line of code here which is swap these two things. Or for each adjacent pair, I and I plus 1. There's very few languages which will recognize that. So this is basically somewhere between describing it in English and describing it in code. So that's bubble sort. Really nice and simple. Let's go back to the laggy camera and have a look. Better not forget the mic. And have a look at some of the... Keep running into my camera stand. And have a look at some of the sort of conditions of bubble sort, like when it's good and when it's bad. So imagine, someone gives you an already sorted array, and you don't know that it's sorted or not, you just want to run the sorting algorithm. So what does bubble sort do in that case? So it checks the first two, finds they're in order, checks the next 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 two, finds they're in order, and stops. Right? So if you give bubble sort an already sorted array, it effectively does the minimum amount of work. And if you're paying attention, you'll notice that that's a lot like one of the exercises that you've done in the labs. Unless I'm confusing this with programming 1 and then the other class did it in the labs. I'm pretty sure you guys did it. So this is the, I think I called it a short sorted check or something like that. And then there was an extension exercise to do it on a long one. That's basically an integral part of how bubble sort works. It iterates along the array, checking for things whether they're sorted or not. Where you guys just had to return true or false, in bubble sort, if it's unsorted, you swap them. And you just keep doing that swap until it gets through and returns false for the whole thing, essentially. So you've actually already seen a good chunk of this algorithm. What happens if we go the other way? So if we start with it reverse sorted, well, you might be able to guess this is in fact the worst possible setup for bubble sort. Because as before, I said what it's kind of doing in each pass through the whole array is finding the biggest element, wherever that might be, and moving it to the end. But it does it one swap at a time. So if we go back to the code for a moment, or the pseudocode, you can see if you don't have to swap anything, then the algorithm's not so bad. It doesn't do all that much work. But if you have to swap something, then you've got to shuffle all these variables around. Individually, that's not a lot, but if you have a really big array and you're doing a lot of swapping, then that's a fairly tremendous amount of work. The comparison itself also costs something, but we'll wait till DSA to talk about the impact of that. So in this case, what's going to happen is it'll swap 5 and 4, swap 5 and 3, swap 5 and 2, swap 5 and 1, swap 5 and 0. Then go back to the start, swap 4 and 3, swap 4 and 2. So you can see that it's doing every possible swap that it can do. So it's not getting to skip any of them. So this is our worst. Oh, I forgot to put the swap there. This is our worst case. So for every single one, it's effectively doing the maximum amount of swaps that it can possibly do. And because of the way bubble sort works, even once it's sorted, you have to go back and check that you're done. And then we're happy and it's sorted again. So that's bubble sort in a nutshell. So just sort of waiting to check if there's any questions about that. So like I said, bubble sort, its main advantage is that the code is really simple. But you can see if your array is in a particularly bad state, then you do a lot of work to get it sorted. So let's look at another sorting algorithm. So I'm going to set this up, then switch the camera over. So the one that we're going to look at now is selection sort. And again, this is one that we've actually been doing some of the code for already, even if I haven't told you that you're doing it. Oh yeah, I'll talk about Stupac in a moment. Well, probably in about half an hour. But so the way selection sort works is that it divides the array into two parts. It has a sorted bit to the left and an unsorted bit to the right. So when it begins, the sorted bit is empty. So everything to the left of this special card is sorted, and the unsorted part is the rest of the array. So what it's going to do at each step, as the little prompt card here says, is it's going to find the minimum element in the unsorted part of the array, and it's going to move it back to the start. So if you have successfully completed the min swap exercise, that's basically what it's doing. And once it's found that minimum element in the unsorted part and moved it back, it can increase the sorted section by 1. So another way of thinking of it is that at each iteration, it's finding the next smallest element and sticking it on the end of the sorted part. Okay. So the way that it finds that is by a loop. So you should be hopefully familiar with how you find the minimum in an array, but let's take a look. So I'm going to mark the first element in my unsorted part as the minimum element. So that's my guess as to what it's going to be. And then I'm going to iterate along the array, comparing things. So you can start here, it doesn't really matter. And you say, is current less than minimum? So if current is less than minimum, then we move minimum to where current is, and then we keep going. So here current is the same as minimum because it's exactly the same element, so we don't do anything. And we keep going. Is current less than minimum? So is 0 less than 3? Yes. So 0 is our new minimum, and we move along. Is current less than minimum? So is 4 less than 0? No. We move along. Is 2 less than 0? No. So we move along. Is 5 less than 0? No. Move along. Is 1 less than 0? No. So we've reached the end of the array. Once we've done that, so once current hits the end and disappears, then whatever minimum is pointing at is the minimum element. So we swap that with the element that is just after the end of the sorted section. So we're going to swap it back to here. So once current's gone, we swap these two, clear these variables for the moment, and we increase our sorted section by 1. So you might be thinking, how do we do this? Well, we can keep a variable that keeps track of where things are sorted, or if you use a for loop correctly, this is basically just the index at each for loop, because you know each time you go through, you're adding one more element to the sorted part of the array. So then I begin the whole process again. So it's still a nested loop situation. Is current less than minimum? No. Move current along. Is current less than minimum? No. Is current less than minimum? Yes. So this is our new minimum. And move along. Is current less than minimum? No. Is current less than minimum? Yes. So this is our new minimum, and move along. So again, we've found the next smallest element in the entire array. So we already found the absolute minimum 0. Now out of the unsorted section, the next smallest element is 1, and you can see min is pointing at that. So we swap those two. So we move whatever our minimum is all the way back to the start of the unsorted section. And move our sorted section up. So now those first two elements are done. And we repeat the process. And by repeat, I mean we go around the loop once again. Anytime you get a repetition in a programming language, what you normally mean is you have a loop. So, we get the stupid one first. Is current less than minimum? No, of course not. Is current less than minimum? Yes. So we move minimum up. And current up. Is current less than minimum? No. Is current less than minimum? No. Move that. So once again, minimum is pointing at the smallest thing out of the remainder of the array, out of the unsorted part. So we swap minimum back to the start there. Clear all of this nonsense. And increase our sorted section. Right, so then we go to the next round of the loop. Current's not less than minimum, we move it. Current's not less than minimum, so the only thing we move is current. Current is less than minimum, we adjust our minimum. Current moves along, it's off the end of the array, so we swap the minimum back to the start of the unsorted section is the same as the end of the sorted section, so you can think of it as putting it on the end of the sorted section. So you'll notice something here. When it did that, it kind of made more work for us because we took the 4 and put it up at the end. There's no great solution to that, unfortunately, but the best we can do is find the minimum and put it back in the right spot. Otherwise, you end up doing bubble, like if you kind of want to maintain the relative positionings, you end up doing bubble sort, and it turns out that costs a lot more than this occasional swap where you end up putting something you don't want up the end. No jokes. Getting near the end now. So our sorted section is now the first 4 elements. So if you wanted to find the however many smallest elements in an array, you can just run selection sort for a fixed number of loops, and you'll get this is the 4 smallest elements in the array. Okay, is current less than minimum? Nope. Is current less than minimum? Yes. Move minimum up. Current goes off the end of the array. We swap down. Increase our sorted section. Now the keen-eyed among you will notice that whatever's left here has to be the biggest element in the array. So we don't actually have to do this thing at all. Once we get the sorted bit up to 1 less than the I guess it's n-2 if this has n elements. 0, 1, 2, 3, 4, yeah. Once we get this up to n-2, then we can just stop because we've got 1 element left and it has to be the biggest thing. So you can make a saving of 1 trip around the loop with that. But we can compare it, that goes there, nothing happens, we swap it, we move that. And then we're done. We now have a nice sorted array. So that's n minus 2 because we don't need the last element. So the last element is still numbered n minus 1, but we can stop when we reach n minus 2 because once we've got one element left, we know that it's already in the right spot. But you don't need to. You can keep going. Like, you can just do that redundant last check if you like. Why is this not working? Hey, there we go. So the code for selection sort looks superficially similar to bubble sort. But it is subtly different. So our input is still an unsorted array. Output is a sorted array. So this one also has nice simple code. Let me do this another way. So I'll add some optimizations here. Actually, that's a nice way of doing it. Okay, so this is basically the pseudocode for selection sort. That's the way I just enacted it then, except for that very last check. So we have an outer loop, which is basically the position. So that outer loop controls this thing here. It controls where sorted is. So sorted starts. Alright, sound might get crap here, I'm leaning over. Sorted starts over at 0 and basically says that the unsorted position starts here and it moves up at 1 each step. So it gives you the start of the unsorted section. And like I said, once the unsorted section starts here, you actually know that you're already done because one element is already sorted and it has to be the biggest just because of the way selection sort works. If it was a different sorting algorithm, that may not be true. It's just a property of selection sort because you're always taking that smallest element. So then for each iteration of marking the end of the sorted section, we say that our min is the first element of the unsorted section, and then this loop in here just iterates along the rest of the array, checking if in fact the min is somewhere else. So you take a guess that it's the start of the unsorted section, and then you check, okay, is it here? Is it here? Is it here? Oh, okay, this is better. Is it here? Is it here? So this little one in here, you've already done in the min swap thing. In fact, basically this bit here is the min swap exercise. So I've put a little condition here that, if you actually need to swap it, swap it. You can just ignore that, like it kind of doesn't matter. You can swap something with itself. It's technically wasted work, but the algorithm is still correct. Then once you've been through every possible iteration of this outer loop, you're done. The array is now sorted. And once again, we're at the end of something. That's selection sort. That's it. It's done. It's a nice simple thing. You'll notice it is give or take about the same size as bubble sort. No one knows what asymptotic complexity is, but they have the same asymptotic complexity, which means as the arrays get really big, they take basically the same number of steps, but selection sort is slightly faster than bubble sort in most cases. Bubble sort has a wider range of behaviors, so its worst case where it's doing every possible swap is really bad, but its best case where it just zooms along the array is good. Selection sort kind of sits in the middle. It always does roughly the same number of things because it only does one swap per outer loop instead of here possibly one swap per outer loop per inner loop. And this bit is relatively cheap. It's just moving a pointer along. So it's still doing that one comparison the same as bubble sort and just doing one assignment. Yeah, so as one of the comments in the chat just said, selection sort basically runs in a fixed amount of time for every pass through the loop. Well, I mean, it gets smaller each time because you're doing one less element. But once you've got exactly the same number of elements in 2 runs of the selection sort, it'll still work the same. Because it still checks every index once. Assignment is pretty cheap, so it's not going to make a huge amount of difference. And it does one swap. Again, you can shave little bits off here and there, but it kind of doesn't matter to the whole thing. Okay, so let's do what we did with bubble sort and look at what happens in different cases. So you might get a bit of a feel why the two algorithms are a little different. Like my change of transition. So what happens if we start with everything sorted? Am I still on the screen here? I need a bit lower for selection sort. So if I start like this, so remember in bubble sort, if I started with it sorted, it just checked, well, these don't need to be swapped, 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 I am happy. Selection sort still does exactly the same work as it does when it is unsorted, or when it's all messed up. Current is not smaller than min, 2 is not smaller than min, 3 is not smaller than min, 4 is not smaller than min, 5 is not smaller than min, gets to the end. It doesn't do that movement of the min pointer, so technically it's doing a smaller amount of work, but it's a fairly trivial amount. So then maybe it does the swap. So if you have that check to see whether you're going to swap min with itself or not, you can avoid doing that extra swap, but you pay for it in doing that check. Normally the check is probably cheaper than the swap, but it depends a bit on your architecture, I guess. So current smaller than min, no. 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 Right. So you can already see that we're kind of doing more work than bubble sort already, because bubble sort did one pass through the array. We've done one pass, and then we have to go back and do the second, and now we're going to do the third. So it always does n-2 passes through the array. It does less work at each pass than bubble sort might do, but it still always does that many passes. So this bounces along. Oop. And then we look at the rest of the array again. Then we look at the rest of the array again. And then, assuming we've written it reasonably well, we can stop at that point. But you can see that difference there. It's always going through the array over and over again, combing through it. The trade-off, so it doesn't have that nice behavior of bubble sort when it's already sorted, but if it's reverse sorted, it's basically no extra cost. So here I have a slightly different thing, so I'm going to keep moving min up then current up, because current is always going to be smaller than min at each step. But that little movement of min is just effectively incrementing another pointer, and is a lot cheaper than the swaps that bubble sort would do in this case. And quite neatly, it's actually going to sort it into the middle. Because if we have it set up this way, it's the smallest one is up the end and the biggest one is at the start, and it's always going to swap those over. So you're actually going to get sorted when you're halfway through. So current is smaller than min, current smaller than min, current smaller than min, current smaller than min. Current is not smaller than min, so we swap these two and trash our array, and whoop, seg fault, just ruined the memory. So that bit's now sorted. Back to here, current is smaller than min, current is not smaller than min, current is not smaller than min. So you can see we're doing one less thing at each step. That's done. That is now sorted. And now we're back to the sorted case. So now, from here on, it's the same as if we'd started with the array sorted. So then, I've forgotten how to split these. Let's put those there. So we've got, which way around it? Selection sort on top and bubble sort on the bottom. You can see that selection sort is in some way, I don't want to use the word stable because that has a particular meaning with sorting algorithms, but it is more steady. It basically always does about the same amount of work. Bubble sort varies more widely, and when it's bad, it's really bad, but when it's good, it's really good. So depending on what you're expecting your data to look like, one may be a better choice than the other. So if your data is mostly sorted, like if you're, say you're reading, this is not a perfect example, but you're getting like TCP/IP data and you're getting numbered packets in, and you're on a pretty good network, mostly the packets will turn up in order and there'll only be a couple that are disordered, right? So you only need to swap, a couple of pairs somewhere along the way, and you can probably do it in one pass through. So bubble sort would be a pretty appropriate sorting algorithm for that particular case. If you're expecting your data to be effectively randomly distributed, so the ordering that it comes in has got nothing to do with its actual ordering, bubble sort is really going to punish you. Something like selection sort is better. So you've got two algorithms that fit in a pretty small space and are pretty hard to get wrong, which is a nice advantage. But they have quite different behavior, and there are reasons for choosing one over the other. Yeah, so if things are roughly in order, bubble sort wins. If it's not, selection sort is better. Yeah, that's a good word, Nick. Consistent. Selection sort is very consistent in the amount of work it does, whereas bubble sort is... you can predict what it is if you know what the distribution of the data is, but it's very broad, not consistent at all. So, just throwing ahead for those who are going that far, if you do data structures and algorithms, you'll see that there are other sorting algorithms which are much, much more complex than this. So if you're willing to pay for a much more complicated code, or it's not the most complicated code in the world, of course, but if you're willing to pay that price, you can get a sorting algorithm that is significantly faster. But you've got that more complicated code that may have other requirements. So... no, I won't. I was going to show you it, but for those who do DSA, it's part of some of the answers, so I shouldn't give it away on the Programming Fundamentals stream. That would be unfair to the people doing DSA. Anyone who comes to talk to me, I'll talk to you about sorting algorithms and show you the other ones. Okay, so for the purposes of Programming Fundamentals, that's our basic introduction to sorting. There are two solid, easy to implement sorting algorithms, which both have use cases, depending on what you know about your data. And hopefully you've noticed, I tried to point it out as we went there, that we've actually already been through sort of the subcomponents of each of these algorithms in the lab. So next week, when you're doing the week 6 required tasks, remember that you've already done some of those bits. So in the required task, as is traditional so far, because the required tasks are just like your bare pass minimum thing, you're going to get a fixed size array. So you could unroll this and do this manually. So if you're getting in trouble, think about the steps that I just did over there and just write them out manually. But if you have spotted, the min swap in here and find the smallest, find the minimum element there, the short sort check exercise there, then you're a long way to writing the proper implementation of these algorithms. And once you get there, they're not actually that hard. So to get full marks, we have to do all tasks or just the required. To get full marks, you have to do all of the required tasks by week 10, all of the additional tasks, which won't start coming out until week 7, and the assignment, which doesn't come out until week 7-ish. So there's a question, which sort does Java implement for its list.sort method? So it implements one called timsort, which is sort of quick sort with some optimizations. So it's actually in the list of sorting algorithms. So for those who are into algorithm stuff, the sorting algorithms page is actually quite fun. So to the source of all knowledge. So TimSort, which is named after Tim Peters, which is pretty good. Just name a sorting algorithm after yourself. Is a mixture of two sorting algorithms, merge sort and quick sort. So merge sort is a very consistent sorting algorithm and is very, very fast. Merge sort and insertion sort. Not quick sort. Yeah, so it uses merge sort when the array is really big, and the way merge sort works is it cuts things in half and sorts the sub arrays and then merges them back together. So that's the merge part of merge sort, because once they're sorted, joining them back together is quite easy. When the arrays get small enough, so essentially when they're small enough to fit in a single page of memory, no, that's too big. To fit in a block of registers, basically, would be the ideal criteria. It runs a sorting algorithm that is technically slower, but works quite well enough when the array is smaller sized, right? Because merge sort, to do all that splitting and merging and splitting and merging and stuff, actually it's split, merge. To do all of that has a cost. Whereas insertion sort works inside the array, so you don't have to keep splitting it. So when you're happy that the array is small enough, the cost of splitting it in half is more than the extra you pay for running what is in principle a slower algorithm. But when it's really big, it's to the advantage to pay that cost to split it in half to merge it together again later, because splitting it in half gives you a big drop in complexity. So the comment repeated, basically when you get insertion sort small enough to fit in cache would be the right way to think about it, because then you don't get any cache misses when you're doing the thing, so you don't have to pull any pages from memory. Just to get like one or two elements of data, you can load the whole thing, do it all in memory, do it in the one spot. You don't have to do any fiddling around with anything. So again, technically insertion sort is a slower algorithm, but because you don't have to pay all that extra sort of secret hidden overhead, it works out faster in those cases. Or practically faster. So I think it's actually used in a lot of places. So it's used in Python, it's used in Java. I think the one in Java is a slight variant as well. I don't remember. Oh, pardon me. I don't remember the exact details, but I think they made some extra optimizations. There was also an issue with it, which was kind of a big splash about a relatively small thing, in that it wasn't actually really broken. It just didn't work quite the way that it claimed. Still sorted everything fine. So if you want to... So there's a way that you could basically bugger things up, that you would never actually really run into in practice. But so I think, so for those who are interested in other ones that are used in various programming languages, I'm pretty sure C++ uses a variant of quicksort, but C++ is weird in that the language doesn't specify what it is. It's up to the library implementer to do it. So I guess it's GCC or G++ implements quicksort, and I think Clang does as well. So I think I can't remember what partition method it uses. Nick might know. But normally there's basically, if you don't know anything special about your data, then normally you go for one of three things. You go for merge sort, Tim sort if you want it to be really fiddly, or there it is, or quick sort. Once you know something extra about your data or you have other conditions, then there's a whole bunch of other possibilities that become available. So if you know that you're only ever sorting small integers, then there's a whole bunch of really cool sorts that work in completely different ways, which are, broadly speaking, all variants of counting sort or bucket sort, but that works in a somewhat different way. Alright, where are we up to? Okay, so that's probably a pretty good time to stop talking about sorting for the moment. So just to finish off the lecture this week, while whatever questions roll in the chat thread, I want to mention what's happening because this is your first StewVac, so you get to find out the wonders of having a week off that you don't actually have time to do anything in. We also have the complication that Easter is next week. So the Easter long weekend starts on the Friday next week. So a week today. So that means there's no classes because it's a public holiday. But anyone who's got a class, then you get relocated to the Friday of StewVac. So I will do the lecture that would normally be on the 2nd of April, will be on the 9th of April. If you've got a lab today, it'll be on the 9th of April instead of the 2nd. Other than that, everyone else, you have normal classes next week and you get the following week off apart from the lecture. Right. So anyone who's got a class on Monday, Tuesday, Wednesday or Thursday, if it's the 5th, 6th, 7th or 8th of April, don't turn up. The building will be open and you can come in, but there'll be no tutor and you'll just be sitting there. Well, I mean, maybe that's fun. Maybe that's what you want to do, but there won't be any class. Yeah, no, there's no homework. So the general idea of StewVac, which is in principle short for study vacation, is that it's a week in the middle of semester. You get another one at the end of semester as well, where you can take a breather from classes and catch up on stuff. So anyone who sets you assignments due in StewVac is a real jerk, because the whole point is that it should be a week where you're kind of free to do the work that's been building up because you've been going to classes and stuff like that. What will I be doing in StewVac? I will be desperately writing as much of the lessons for the rest of the semester as I can get out, so that I don't have to do it week to week like I've been doing at the moment. So I managed to get a few of them in order before there, and then the whole thing catches up with you, because the lecturers get in the same position as you guys, where everything builds up and then it's like, get it done, get it done, get it done. I will also definitely be drinking plenty of tea. That is a given. Was there anything else? I think that's pretty much everything for this week, so unless there's any questions, we can stop that there. Everyone can take a short break before their lab, head off to your normal Friday lab, and I'll see some of you on Tuesday. I won't see you next Friday, I'll see you the one after. Oh, BOGO sort. Yes, sorry. The special thing for everyone who sticks around. I'll show you BOGO sort. Okay, back to the thing. Nearly forgot about BOGO sort. Okay, so BOGO sort, let's randomize our array. Kind of doesn't matter what it is. So am I all on screen there? I was about to write a card for it, but let's leave that. So BOGO sort works by starting with the full array in whatever state it comes in at, then randomly shuffling it, and hoping desperately that it's sorted. So we've got 3, 0. Oh, it's not sorted. Okay, it's alright. BOGO sort still works. So if it's not sorted after the first round of shuffling, shuffle it again. Is it sorted now? Nope. Okay, it's alright. Shuffle it again. Alright, shuffle it again. Oh, that's actually almost close. But that's BOGO sort. So BOGO sort is, just in case it's not obvious, is a joke algorithm. So it is the sort of canonical worst possible algorithm that still technically works. Quantum BOGO. I don't think I can do quantum BOGO sort with real paper. So for those of you who do go onto DSA, there's a really nice sort of exercise in working out what's the largest deck of cards that you could sort using BOGO sort, like possible ever. So anyone who gets that far and hasn't worked it out by then, come and talk to me, and I'll take you through the demonstration of exactly how bad that algorithm is. But you need to know stuff from DSA for the explanation to make sense. So I think there was a there's one in there that was, what's the best sorting algorithm? So the best sorting algorithm is the one that fits the condition that your data is in. So it's not one single one. If you know absolutely nothing about your data, I am personally very fond of merge sort. It works extremely well in almost every case. The trade-off is that merge sort requires a fair bit of space to use, and if you don't want to use that extra space, then it gets really complicated and really fiddly. If you know that you're searching small integers, radix sort is fantastic. So it doesn't do it by comparing the numbers, it does it just by looking at the digits of the number in whatever base you want, but say in binary, and then just partitioning things. And it's kind of a weird bit of magic to see it work, but it is a pretty awesome sorting algorithm. But it has limitations, like if your numbers are too big, or you've got, well, not the number of numbers, but the size of each individual number. If that's too big, it doesn't work effectively. Whereas merge sort always works pretty effectively in every case. And merge sort is almost always really fast. I'll see if I can find, just to do the last bit. There used to be a bunch of websites that did this, but they seem to be going out of fashion. So I'll see if I can find one that works, especially with all the crazy script blockers that I've got installed. Okay, so assuming that this works, so I'll move the animation speed up a bit. So this is selection sort, the one that we just saw. So this is sorting 100 elements, I think, something like that. So you can see it's obviously this is slower than it is in on an actual computer, because it's sort of doing it visually and it's stepping through in a way that you can actually see. So this is much faster in practice. But you can see how it's working. It's putting that smallest element there each time. I might have to go all the way to the end. But in comparison, let's take a look at, so merge sort on the same data. So watch this one carefully. So it looks like it's doing a bunch of stuff, but you can see it gets these big bits where it just kind of goes blam and sorts it, and this last bit will be done. So if you're timing that, you'll see that's significantly faster than selection sort. So quick sort, depending on the state of the data, is also very fast. It's a bit like bubble sort in that it is sensitive to the distribution of the data. Merge sort isn't. So merge sort, like selection sort, is very consistent, but it also happens to be very fast. In the right situations, quick sort is extremely fast, but in the wrong ones, it's quite slow. So you can see that one was pretty good. Now this is already sorted. That's not going to be interesting. Oh, there's a randomize array button. So bubble sort. You can see it's pretty slow. So the way quicksort works is it partitions the data, like it picks something to partition the data with, and how you pick that is the key to making it work fast. And puts all the things that are smaller to the left and all the things that are bigger to the right, and then recursively sorts each section. So you can see bubble sort, it's pushing each one up there. So you can see here, even though there's only a tiny bit of work to do, this 3 can only go back one step at a time till it gets there. But when I run that again, done. No, it goes through twice. Wait, this is a bad implementation of bubble sort. But just to do it again, if you look at merge sort, so you can see it's using this, it may not be obvious what it's doing, but it's using this extra space down here. But you can see it's basically sorted half the array already. There's the other half, and then it puts it back together and you're done. So merge sort, really, really good. Okay, so that's our time there. So you'll run into those algorithms and data structures and algorithms if you go that far. So you'll definitely see merge sort, insertion sort. You'll see selection and bubble again very briefly. Quick sort. Depending on who's teaching it, they might show you counting sort and radix sort, or shells. No, not shell sort. Bucket sort, something like that. Oh, heap sort as well. So heap sort works well, but you need to create a heap. But you don't know what that is, so I won't tell you. Okay, any last questions? Alright, so what does merge sort use to sort inside the clusters? It uses merge sort. So merge sort takes the array, splits it in half, and then runs merge sort separately on each half. If that half is still too big, it splits those in half and runs merge sort on the now 4 quarters, and then the 8/8ths and the 16/16ths, all the way down until it gets 0. Like if you just do pure merge sort, until it gets arrays that have 1 or 0 elements, which are by default sorted. Then the magic in merge sort is when you've got 2 sorted arrays, you can build one bigger sorted array that contains the data of both, by sort of starting at the front and picking the smallest out of the 2 to go into the other array, and then you work your way along those. If I have enough time, I might throw doing the merge in as just an extra exercise in one of the labs, just so you can see what it's like. Not worth marks or anything, just to have a go at it. Because you actually know enough to write the merge part of merge sort now. I mean, technically you know enough to write merge sort, but it'll probably, for most of you, if this is where you started programming, it would be very confusing at the moment. Alright, well, thanks everyone for coming out on this Friday evening once again. Share, like, and subscribe. Buy a Casper mattress for some reason. Comes in a box and explodes, as I understand it. Keep it away from pets and small children. Something Mac Weldon. MeUndies, Dollar Shave Club, something. I don't know. Still none of them are giving me money. I try every week, but I don't know. Alright, have a nice weekend, everyone. See most of you next week, and for those on Friday, you get to start your holiday a little bit early, but then everyone's gets ruined at the end with the lecture, so you get to get it back on them. Yeah, I am amazed Raid Shadow Legends hasn't reached out yet. Like, come on, I'm streaming something. You're giving it to everyone else. Sure, it's unlisted and it's for educational purposes, but who cares? Okay. I'll stop the recording there. See you all later. Have a good weekend. Talk to you soon.